When you hear the word matrix, it is easy to picture some impossibly complex grid of math. But out of all the topics you will tackle in higher-level algebra, this is actually one of the most straightforward. Think of a biscuit factory. To make thousands of identical cookies, they use a mold to shape the dough. A mathematical matrix is exactly that, a structural mold. Instead of shaping dough, a matrix shapes data. It is simply a rectangular box, usually drawn with standard parentheses or square brackets, used to neatly organize numbers, variables, or equations. The individual items sitting inside this box are called entries, and they are strictly independent. You will notice they sit side by side with absolutely no comma separating them. Think back to solving algebra equations with an x and a y. Usually those letters stay the same, while the numbers in front of them do all the heavy lifting. A matrix lets us set those repetitive letters aside and group only the leading numbers into a clean grid. This creates a highly efficient filing cabinet for the data and equations you already know how to use. To use that filing cabinet, we need to understand how it is built inside. Picture a multi-story apartment building. The horizontal, flat lines of data are called rows, exactly like the different floors of the building. The vertical, standing lines are called columns, much like the individual stacks of apartments running from the ground up to the roof. Once we know the rows and columns, we can find the order of the matrix. This tells us its exact size. For example, a matrix might have 3 rows and 2 columns. We write this mathematically as a 3 followed by a multiplication sign and then a 2. But we read it aloud as a 3 by 2 matrix. It is identical to how a carpenter takes measurements for a table and calls it a 6 by 4 piece of wood. There is a quick shortcut here. If you actually multiply those two numbers together, 3 times 2, you get 6. That tells you the matrix holds exactly 6 entries inside. By counting those rows and columns, we define the physical boundaries and the total capacity of our data structure. This is a diagram showing the blueprint of a matrix. Because every entry has a specific address, we use a general formula, written as a lowercase a with a tiny I and j next to it, to act as a GPS coordinate system. In this system, the I always stands for the row number, or the floor of the building. The j stands for the column number, or the specific flat. If we want to find the entry located at A12, we simply look at the very first row and travel across to the second column. Where those two lines cross is our exact entry. Often, equations are given that use these I and j values. By plugging the row and column numbers into those rules, we can automatically calculate the values for every single empty room in the building. This notation can look intimidating at first glance, but it is really just a precise set of directions. It guarantees that no piece of information gets lost in the grid. Matrices come in a few specific shapes. A matrix with only one single row is naturally called a row matrix. If it only has one column, it is a column matrix. And if a matrix is just a single number sitting by itself, it technically qualifies as both. When the number of rows and columns are unequal, you get a stretched out shape called a rectangular matrix. But when the rows and columns perfectly match, like 2 by 2 or 3 by 3, you get a perfectly symmetrical square matrix. A square matrix is unique. It is the only type with true diagonals. The top left number is the leading entry. The line cutting across the center is the principal diagonal. Turning every number outside that diagonal into a 0 creates a diagonal matrix. Identifying these physical shapes is critical. Once you know a matrix's shape, you instantly know which mathematical operations you are allowed to perform on it. If the numbers on that diagonal share the exact same value, it's a scalar matrix. If those numbers are all 1, it's the identity matrix, represented by I. It behaves like the number 1 in multiplication. Anything multiplied by it stays exactly the same. Similarly, if every single entry across an entire matrix is a 0, we call it a 0 matrix. Just like the number 0, adding it to another matrix doesn't change the original values at all. Transposing a matrix means picking up its horizontal rows and turning them into vertical columns. The entire shape flips, turning a 2 by 3 matrix into a 3 by 2 matrix. If you transpose it a second time, it simply reshuffles directly back into its original starting form.